So today we're going to talk about chemical reactions. And we learned way back when we were talking about Dalton's atomic theory that one of the parts of his theory was to talk about what happens to atoms in chemical reactions. And he said chemical reactions occur when atoms are joined, separated, or rearranged. And he followed that up by saying that the atoms of one element cannot be converted into the atoms of another element by chemical reaction. And this is not a subtle statement. Essentially what he's saying here is chemistry happens, or chemical reactions happen, when you rearrange the Legos. And there's nothing more mystical in it than that. It's kind of the final death blow to alchemy, to say that all you're doing is rearranging them. And when we think about joining, separating, or rearranging atoms, what are we really talking about? Well, we're talking about chemical bonds, right? Ionic bonds, covalent bonds, metallic bonds. And that what's really going on in chemical bonds, of course, is that you're rearranging the electrons. So the arrangement of electrons are the things that predict the chemical behavior of substances. Protons and neutrons talk about the identity of an atom or its nuclear properties, but electrons dictate the chemical properties. So here's a really good example of a chemical reaction. So you can think about what happens in a glow stick. So a glow stick has two fluids separated inside a tube. One of them is a hydrogen peroxide solution, and the other is what's called a phenyl oxalate ester, and a dye that is going to get activated when this chemical reaction takes place. So if you look at the chemical reaction to the right, the phenyl oxalate ester is that big structure that's got the two six-sided shapes on it, and then the O's and all the lines. So this is a form of showing organic compounds where every place where two lines meet, there's going to be a carbon and some hydrogens there. So you have these two ring systems, you have a bunch of carbons, you have a few oxygens, and when they react with the hydrogen peroxide, which is H2O2, the system is going to break in pieces. And so we can kind of track where everything's going. So notice in the center of that structure there are a series of oxygens. So 4 oxygens. Well, you have 2 of these rings now have been separated, and then one of the oxygens on each side is going to then attach to one of the hydrogens from the hydrogen peroxide. And that bit in the middle, so remember wherever lines meet there are carbons, so there are your 2 carbons. That bit in the middle is going to form a ring system. So this square situation here. That structure then reacts with the dye. It breaks into 2 CO2s. So you can kind of see if we cut it across the middle horizontally, you're going to have 2 oxygens and 1 carbon, and that's going to double up. And then that activates the dye. That's what the asterisk there is telling you, that the dye is now activated. And so when that dye is activated, it's going to then go back down. So activated just means a high energy state. High energy states, of course, are hard to maintain. So the dye is going to go back to its low energy state, and it's going to also have this thing here, H. And it looks like a V, but it's really the Greek letter nu. And again, we have to go way back to stuff we learned last semester, that H nu actually means the energy of a photon. That's the light given off associated with a certain wavelength of the dye. And so all of this happens, right? You've got these 2 substances separated. And of course, there are very few experiences more satisfying in the world than breaking a glow stick. And when you break that interior cylinder in the glow stick, those 2 solutions mix, and it starts a cascade of the rearrangement of atoms. And wonderful things, of course, happen. You get a glowy situation that you can swing around in the air and make shapes and lights and colors. And they're exceedingly fun. If you don't think glow sticks are fun, I'm a little bit worried about you and your childhood. All right, so that's a chemical reaction in a fairly complex version of a chemical reaction. Let's look at the general format of a chemical reaction. Chemical reactions start with reactants on the left. Those are the things you mix together. The arrow represents some process reacts to form. and then you get a series of products. And so the structure looks like this, where the lowercase letters are meant to be how many of each atom, and the uppercase letters are to represent particular substances. And so the A, the capital A, capital B, capital C, capital D are chemical compounds or elements, and then the lowercase letters are what we refer to as coefficients. They're how many of each particle needs to react. And so let's look at an example. So here we have a chemical reaction in which 4 aluminums react with 3 oxygens to produce aluminum oxide. And so these numbers again represent the coefficients. Aluminum and oxygen are your reactants. Aluminum oxide is your product, so we're forming an ionic bond in this case. And then here we have the physical states. So here we have solid aluminum is reacting with oxygen gas, probably in the presence of some heat, to produce aluminum oxide solid. So let's talk about interpreting this chemical reaction. So there are several ways to interpret a chemical reaction. One of them is to talk about interacting particles. So think about the representative particles that are involved here. And so we might talk about how 4 atoms of aluminum are going to react with 3 molecules of oxygen gas to form 2 formula units of aluminum oxide. And so notice the types of representative particles can change as different types of bonds form. But of course, if you are watching this reaction take place, if you've measured out the aluminum that you're reacting with the oxygen, you're not dealing with individual atoms because atoms are too small to see. You're seeing this process play out with billions and billions and billions and billions of atoms. So another way to interpret a chemical reaction is in interacting moles. So we can say 4 moles of aluminum react with 3 moles of oxygen gas to form 2 moles of aluminum oxide. So there are a bunch of symbols there that you should certainly be aware of, and some that will point out but you don't necessarily need to know. So the first one is the arrow, which means yields or reacts to form. That indicates the transition from reactants to products. If you take Chem 2, we'll talk about what are called reversible reactions, where you can form products, but then the products can then recombine to form reactants. But we're not going to worry about that in too much detail right now. There are 4 states of matter to be aware of. And so things that react in solid state, we put in parentheses, generally subscripted, an S. If you ever see a down arrow next to something, particularly if there is, again, if it's a solid formed as products, that is what we refer to as a precipitate. And a precipitate is when you mix 2 solutions and the solutions produce a solid because one of the products is for some reason insoluble in water. So a down arrow is another way to designate a solid product. So you wouldn't do that with a reactant, you would only do it with a product, and it means that you're forming a precipitate. Things that react in the liquid state or are produced in the liquid state get an L. We'll skip over that next one to go down to gases, so things that react or if a gas is produced is going to be a G. And then when you dissolve things in water in order to get them to react, we refer to that as an aqueous solution, or AQ. So things dissolved in water get an AQ rather than a liquid because it's what you've dissolved in the water typically that's reacting, not the water itself. You can see below the G, much like if we produce a solid out of 2 solutions, we get a precipitate. If you produce a gas out of 2 substances, we'll sometimes put that up arrow. Again, the up and down arrows are only used for products. If you need a particular amount of energy in order for a reaction to take place, we're going to put the Greek letter delta above the arrow, and that indicates that heat is needed, or sometimes you will in fact just see the word heat. In general, if there is a particular reaction condition that you want to bring to your reader's attention, you'll just write it above the arrow. So various pressures or temperatures that are critical to the reaction, you're often going to see written above the arrow. We're not going to worry about that too much in this context. We're going to keep things fairly simple. What you do need to know is if you ever see a chemical substance written above the arrow, that indicates the presence of a catalyst in the reaction process. And a catalyst is something that allows you to speed up a reaction, but it is not used up in the reaction, which is why we write it above the arrow instead of writing it as a reactant or a product, because it's in the ultimate process, the elements don't get rearranged. Their chemical bonds remained intact over the course of the reaction. So there's a bunch of ways for catalysts to work. Sometimes they donate electrons to the process but then recapture them. Sometimes they bind to one of the reactants temporarily but then again are disconnect from the product and then are there in the same form that you started with before the reaction. So a catalyst is something that speeds up the rate of a reaction without being used up. So in this case, magnesium dioxide is being indicated as a catalyst, but it could, of course, be any substance written above the arrow. And those are some basic symbols that you need to be aware of in chemical reactions.